Hello and welcome to an unusual video for my channel. I will be sharing my preliminary analysis of competitive Team Fortress 2 using network science techniques. If you've been following my channel at all, you probably know I play Team Fortress 2. I also have a project to do for a class that I am taking on network science. So, as usual, I ask myself, can I put the two together? The answer in this case is yes. Wait, this is the wrong project. Before we begin, an introduction to both competitive Team Fortress 2 and network science is in order. Team Fortress 2 Sixes is a competitive format where 12 players are split into two teams, red and blue, spelled without an E. On each team, there are usually two scouts who are agile, sporting a double jump ability, but have low health. There are two soldiers. They deal moderate damage, but can use their rocket launcher for mobility. To support this bad idea, the soldier has greater health. And there's one demo man who specializes in area denial and has the potential to deal huge amounts of damage very quickly. Lastly, there's a medic who can grant invulnerability to their teammates after charging an Uber ability through healing. This Uber ability is a primary driver of tactics in the game, making the medic a valuable target. The objective in Team Fortress 2 Sixes, at least in our case, is to capture control points. Each map has 5 of them. 2 are owned by each team to start, with a midpoint pictured here owned by neither. Usually, 5 control point maps have rotational symmetry about the midpoint, which can be seen in this picture here. If we look at the rock in the back and the rock in the front, we can see that they are the same rock. Pictured here is the map CP Process, which is a map played very commonly in newcomer circles to learn fundamentals. This map will also be the focal point of this preliminary study. Now we move on to network science. Network science is the study of phenomena that appear along networks. Some examples include studying social interactions through social networks. Pictured here is a visualization of the closeness centrality calculated along the dolphin's social network. We can also do epidemic modeling. Pictured here is the potential spread of a computer virus via Bluetooth. Epidemic modeling is also commonly applied when studying pandemics, including COVID-19. As a resident of the Western U.S., an interesting application of network science that I'm particularly interested in is studying spreading phenomena such as wildfires. Pictured here is a visualization of the spread of a digital wildfire, represented in black, on a specific model with a set percolation coefficient. However, the models we are working with today rely on a more basic interpretation of networks. At its root, network science is about the study of networks themselves. Let's construct an example network before we dive in. First, we have a set of nodes. These can represent whatever we want. Airports in the transportation network, for example. Then, between them, we connect them via edges. In our airport example, edges may represent the scheduled flights between 2 airports. Secondly, we can set attributes to the nodes. In our airport example, this may be the size of an airport or the number of runways, but here we'll just set a cool factor attribute. Edges can have these attributes too, but importantly, we can also give them direction, meaning travel in one direction is possible, but direction the other way may not be. In the real world, there might be a flight from Boston to Tallahassee, but maybe not a flight in the other direction. An edge attribute in our air travel example might be the amount of fuel used for each flight, or the number of passengers. We could also set both by having multiple attributes. Now that we have covered the basics, we can begin combining Team Fortress 2 Sixes and network science. Let's consider this network. It is of a Frank Lloyd Wright building. Each node, the dots in the diagram, represent rooms, and the edges represent adjacency. In other words, is there a doorway that connects the 2 rooms? The author of this diagram also labels the nature of the edges. The jagged edges in this case represent stairs. Using this same framework, rooms connected by adjacency, we can convert a Team Fortress 2 map into a base network. Pictured here is my attempt to convert process into a network. We will use this network in our future analysis. To create this network, we first split the map into quote-unquote rooms. Those of you who have played the map know that there are multiple nodes in each actual room on the map. This is because the rooms themselves are too large. Just tracking each room without any notion of where you are in the room takes away too much information. Fortunately, most competitive Team Fortress 2 players use a system of callouts to make it easier to communicate and strategize, but even this has its limitations if we just use callouts. To end up at this network, I used callouts as the base and then split it up further based on where the edges might go. This allows the network to be clearer in regard to location within the rooms and the paths that can be taken to and from those locations. Each edge here represents whether or not you can get from one node to the other, adjacency, like in the previous slide. Hence, we have nodes that function like combinations of a few areas on a navigation mesh used by bots. The method used to create that navigation mesh could be modified to prepare maps for analysis in the future, as it tracks walkable areas and their adjacencies. Lastly, we utilize map symmetry to label the other side. Blue spawn is labeled 0, and the midpoint around which we rotate is labeled 47. So red spawn gets the label 47 times 2, which is 94. We can use this to index the nodes on the other side by taking 94 and subtracting the value on the blue side of the map, which I got used to while collecting data for this project. Speaking of which, in order to use the network for game analysis, we need to collect data that represents people playing the game, moving from node to node along the network. Fortunately, many competitive Team Fortress 2 games are recorded via demo files, and competing in various circles such as RGL requires you to record demos of your matches. Many demos, such as the one I use here, are available from demos.tf. To record the data, we want to track where each player is over time, so first we pick a tick resolution. For this project, since I was collecting data manually, I set a resolution of 200 ticks per frame. With this, we collect data once every 3 seconds, approximately. Then, for each tick that we want to collect data, we write down the location of each player to apply to our base network later. We just need to track the node that they are in the area of. For additional context, I also wrote down the score, because each game happens over a series of rounds, and the game state at any given moment, basically telling us which points have been captured by either team. This always starts with the mid-fight pictured here, but once the midpoint is captured, it alternates between red and blue second or goes to red or blue last, depending on how the game plays out. Before we do any analysis, we need to make sure we got the information we wanted, so let's visualize our data by getting a video of the game being played on the network. At each tick we recorded, we make a copy of the network and set some node attributes. First, we track the number of players at any given node, which will govern the size of the node in our visualization. Then we track the players on each node by saving a list of their tags, which we used in the data collection process. We also track which team has control of the node, which will govern the color in our visualization. I set the color to whichever team had more players on the point, or yellow if none, or purple if the number of players from each team on each node was equal. Then, we draw each network and save the image generated. By playing the images in succession, we can watch the game play out on our little network. While the video plays, I would like to point out what we have just done here. We've taken a demo file that uses continuous coordinates to track player location and changed it to a discrete list of nodes where they can be. In effect, we have done some sort of dimensionality reduction. In reality, this method of storage seems simpler, but the processing takes much longer because creating a network at each time step to do analysis takes a long time. Luckily, as we'll see, for some metrics we can bypass this step entirely, but there are some future directions I may take with this that may require the processing to happen. For now, this is the most complexity will go as far as computation is concerned. Onto the analysis part of the video. Let's consider a couple questions and see if you can figure out how we might use this network representation to answer them. From a mapper's perspective, and I am a mapper myself, how can I find out which areas of my map are unbalanced and need improvement? From a coach's perspective, and having been a team leader myself, how can I find which map locations my team struggles with? For both of these questions, it is important to look at the way players move along the map. If more motion happens in one direction through one area, either the map is imbalanced in said area, or the team on one side is having trouble or can't stop the other. For this, we need to consider the flow of players along the network. Network science gives us a great tool to start with. Each player, when moving from node to node, generates a walk along the network. This walk also includes direction. So, for our network, we can add an attribute to our edges that represents how often they were walked over and in which direction. There's just one problem. What do we do when a player appears to have gone from one node to another node that is not adjacent? There are a couple cases of this. For example, a fast-moving player, such as a rocket-jumping soldier, may skip over a node between two ticks where we record, which happened pretty often in my case. Or, a player can perish on the midpoint but spawn all the way back by last, creating a teleportation where we do not want to record anything anyway. The solution is simple. Once we have an algorithm that works to collect the data along walks that go from neighbor to neighbor, we can add a filter that checks for adjacency. If two nodes on our walk are not adjacent, we can calculate the shortest path between the two nodes and send the resulting path, which will be a walk that goes from neighbor to neighbor, back into our original algorithm. This is our recursive case. To detect spawns, we can add a dummy node value of -1 to our walk at each time step where the player who is walking is deceased. Then we can detect when our walk hits that node and simply not record it. If a player spawns in one spot, but has the opportunity to forward spawn, we can use a similar solution to detect if the walk intersects a forward spawn and ignore that edge. Here are the results of our work on the previous slide. I've set the arrows to show which direction was traveled more, with the width representing how much more. We can see the thickest edges are along the player rollouts, where usually movement is not impeded as players move from their spawn area to the area being contested. We can also notice that IT is more commonly used to get to mid, rather than go from mid, and sewer is the opposite. There's also a lot of movement to low ground, such as the valleys between second and choke. Control points are also focal in this way. On the right, I've filtered the data going into this graph to consider only the scouts. Can you spot the differences? Lastly, can we improve on these graphs? Of course we can. For example, we can add information to the nodes by considering how often each was visited. This is even easier to calculate than the flow. We just add 1 to each node's visits attribute whenever a player visits along its walk. And here are the results. As we can see, some spawn rooms are focal. Red last, for example, there was a lot of off-classing when the fight came to last, and to change class, you need to be in a spawn room. This is especially apparent in the scouts only graph, because scouts are the most likely to off-class during a match. We can also see that while mid is a focal point as expected, the second points are less focal than the areas around them in that they aren't stood on the most often. Last points are more odd, because players usually defend from the right side when looking from spawn, but don't necessarily divert a lot of resources to the left. So we see a gradient of number of visits to each node from right to left in the areas around last points. There are issues with these techniques. First, we know that movement from spawn rooms along rollouts skew the results. We want information about balancing. Keeping data where we know there will be no contestation doesn't make much sense. From the coach's perspective, we also don't get the full picture. We can see that the red team struggled around second due to the increased presence between red second and mid over the course of the match. However, we don't know whether or not this is because blue struggled to attack second or because red struggled to push back to mid. From the mapper's perspective, we have the same issue. However, we also want more data to weed out the noise from potentially imbalanced teams. We can easily double the data by rotating the graph about the midpoint and summing the attributes, but ideally we want it over the course of multiple games with multiple players. Lastly, I noticed that normalizing the attributes by the sum of all, so that they represent a fraction of the total visits or traversals, would have made for a better representation. In the last part of this video, I would like to show you the future of this type of analysis. Some feasible next steps include detecting choke points and finding areas of deathmatch disadvantage. What I am most interested in is improving the flow analysis, or most visited representation, for its usefulness to players and mappers alike, along with necessary automation to make it happen. To do this, we need to automate the network creation and automate the conversion of demo files to represent along those networks. I originally planned on looking at multiple games and maps for this project, but I ended up resorting to a single game because of how darn long it took to collect by hand. Another possibility, if we can automate the data collection and conversion, would be to create a tool for coaches to get the flow diagrams in order to better help their teams, and for mappers to have a quick visualization of how their map played during a testing session, such as those hosted by TF2maps.net. Other possibilities include detecting player division. Can we make a model that can classify a player's skill based on this type of data? Nodes can preserve location information on a similar level to how they are in normal demos, but the dimensionality is reduced, meaning a model made using these types of techniques could be more efficient. This model could also be used to catch Smurfs, who are skilled players who create fresh accounts to play in lower divisions. Using similar techniques, we could detect vantage points. I think this is a side grade, if you will, to the current study, as vantage points relate very heavily to line of sight. Recall from the network we made, you can see sewer, which is node 29, from rollout, node 18, but these nodes are not adjacent. In fact, you need to pass through at least two other nodes to get from one to the other. To detect vantage points, we would need two different networks, creating a multi-layer network. We'd have our network that we created as one layer, and a network based where the edges represent line of sight on a second layer. With this, vantage point detection may be feasible and useful to mappers. A combination of the above two techniques may be able to make a good anti-cheat, and I have some more ideas on that front that I will not share here. Of course, we could also develop similar tools for other games. Anyone else looking to do a project like this for another game is welcome to reach out, and I'll gladly share more of how I did it. Lastly, we might be able to improve bot function by having it make movement decisions on the level of our simple network. I think having a bot respond to the subgraph represented by the nodes of its teammates and their neighbors may be a great way to have bots act like they are listening to callouts and move with their teams more effectively. As we know, bots in general are not very useful as they are right now. We have reached the end of this video. Thank you for watching this atypical Spock 13 production. Lastly, while I share some of the resources I used, here is my call for help. I will be continuing this work, namely trying to work with demos directly and improving the flow analysis tool, and would love some assistance creating a tool to automate the map level network generation. If you have the skills, aren't scared of learning how to nav generate, and would like to see this type of analysis developed further, please reach out. Thank you.